having all of this, condensing the means-based stuff together is that a lot of this ends up just being kind of review of stuff that we did not so long ago last semester, which I think is nice. So we had talked about follow-up tests for this one-way repeated measures ANOVA. Go through selecting our contrasts, right? Again, talking about linear contrast standard sets. We're setting up your contrast weights the same way as we had last semester, right? And so again, we're not going to worry that if you get deep into methodology, stuff like that, people will start talking about orthogonal contrasts and things along those lines. That gets into sort of some of the nerdy, like sort of nuts and bolts of experimental study stuff. If you have occasion to get into that, that's cool. We're not going to worry about it for here. Just wanted you to get a basic sense for. These are my contrasts. These are the things that I put this study together for in the first place. This is why we're doing it. This is how we go through and test some of that. So we've talked, presented for your repeated measures contrasts. Okay, repeated measures contrast. Your value of your contrast is just some of the weighted means involved in that contrast, and then your test statistic is just your the value of your contrast over the sum of your squared weights times the mean squared error from your overall ANOVA table divided by the number of people you have in your sample. Okay, and then again testing this against a critical T degrees of freedom error taken from your ANOVA table. So and again, this is if you have contrasts that involve more than 2 repeated assessments, right? I want to take these 2 assessments and compare them against the last 3 assessments or something like that, right? Let's say we have some sort of multiple baseline study where we have baseline, treatment, right? And we want to test the 2 baseline conditions against the 3 treatment conditions, something along those lines. Nice to have these contrasts in your back pocket. We have to do this by hand. SPSS won't do within subjects contrasts for you. But sometimes some of the contrasts that we're interested in are just pairwise comparisons. And again, if that is the case, and you've got big concerns with variability types of situations and are concerned with assumptions, always okay to fall back on paired t-tests if those are consistent with the types of questions and are testing things that you are interested in testing, okay? And again, if these are a priori, convention says that we test these at per comparison error rates, but if you want to be conservative, for a small collection of tests, Bond Peroni doesn't sit out just to go through and test some of these, provide some extra control for that, okay? Feeling comfortable with, and we'll walk through examples so you guys have a sense for some of this, but feeling okay with contrasts? All right. So as we talked before, again, traditional approaches, we're going through calculating contrast, pairwise comparisons, pulling error terms from our repeated measures ANOVA table. Again, this is a more powerful test. It's a classic approach to how we would go about doing this stuff. But again, always remember that anytime we're just pulling summary statistics out of that ANOVA table, the omnibus ANOVA table, what we're doing is we're assuming some very specific things about that design, about these data. And as we start to have problems with violations of homogeneity of variance, sphericity, discrepancies in our cell sizes, if we have a repeated or a between subjects factor in this, it starts to make some of these assumptions less and less tenable. And so we're running tests based on assumptions that we've violated. And so what happens is then we start to worry about whether the conclusions we're drawing from our inference tests are accurate in this, okay? So even though these are the, so we're going to go through procedures for how we would go through and run some of these analyses. Remember that if you've got violations, discrepancies in cell sizes, things along those lines, paired sample tests are always something that you can reasonably fall back on. You lose, particularly for between subject stuff, we lose some power, right? Because we're not pulling our degrees of freedom error from the ANOVA table. We're just saying these are the groups involved, and so degrees of of freedom are smaller, which makes our critical values larger, right? And so they're more conservative tests. But at the end of the day, I would rather go more conservative than use a bunch of procedures that have violated all the assumptions, and so I'm finding stuff when I probably shouldn't be finding stuff, or I don't have confidence in those different tests. Okay. Questions about sort of the general concerns, right? Because again, whether it's between subjects designs or within subjects types of stuff, what you often see if you look through methodological textbooks that have a bunch of like summations and sort of like math-based stuff, they say, oh, well, for this design, for this Latin square, you're pulling this from that and this from that. Perfectly acceptable and cool ways to go about things, but these are oftentimes assuming very specific things about your study, that you have balanced set, that you haven't violated homogeneity of variance, that you have continuous measures, a lot of different stuff that in application we often don't meet. And if we're running procedures, we're using the wrong tool for the stuff, right? So we're saying, oh, we found significant test. Well, yeah, if we'd have confidence in that test, if we had met all the assumptions, but we violated all those assumptions, so now I really don't know how accurate or consistent this is. So if you find yourself in that situation, pairwise tests are something that you can fall back on. Okay. Yeah.
So like basically so far it's like we do our own this test, we get the F, calculate like generalized data squared around that, and then for like follow-ups we do linear contrast, use the t-test to get here.
Yeah.
And then we think there's like a lot of violations of stuff, just use like pairs and like,
yeah. Yeah. But again, and so this is why it's important, and I want you to understand kind of what's going on with this, because your approach, two different studies, exact same design, your approach might be completely different based on what the data look like, right? And so, if my hypotheses are that my two baselines are different than my three treatments, then I can't use a pairwise, right? On that, right? I'm kind of stuck with my contrast. Now my contrast is assuming some stuff, but what I hope you would do is recognize, like, okay, I need this test in order to test the hypothesis that I want, but I've got some concerns on assumptions, and so I would use that to kind of maybe moderate what I found. If I violated all my assumptions and then run the test and it's just barely eking over these P049 or something like that, try and be modest in terms of sort of the extent to which the data are supporting your specific hypotheses, and that, yeah, it looks like it's trending the right way, but we violated a bunch of stuff. I don't know, this is a marginal call. I wouldn't say with 100% certainty and confidence that, oh, this is a home run win for me in terms of my hypotheses. Anytime we get a marginal effect like that, you probably shouldn't be thinking it's a home run support for your hypotheses, but particularly if we violated all of our assumptions. Right. Oftentimes in applied statistics, what we're doing is we're choosing the least bad option, right? And if I need to have a contrast in order to test my hypotheses, you should certainly do that. But you should also recognize the limitations of that, and sort of those violations start to erode my confidence in the accuracy of this test. Now, if it's a massive effect, then it's probably not a huge deal, right? If your effect size is like this, it's p less than 0.001, then probably less concerned as long as you don't have like one or two weird cases driving that whole thing. But as is often the case, if we're down to, like, boy, it's kind of right there on the edge, that's where we start to become a little more concerned. So, concern or questions with any of this?
Probably cover it, but then like
Yep. And we'll go through some examples and sort of show you how you go about this. But again, what makes these analyses difficult, one of the things that makes these analyses difficult is there's no, like, this is the way you do it, right? There's no, this is the procedure you go through. That's going to be based on your design, based on your data, based on your hypotheses. And so this is why it's important to say, all right, this is my approach. This is how I'm going to move forward and address and start to pull this stuff apart. All right, so those are our planned contrasts. We also can look at all possible pairwise comparisons for our excuse me, in our one-way repeated measures ANOVA designs, you can actually do this pretty easily. In the options window in your repeated measures, if you select options in your repeated measures window, you'll see a box you can check, compare main effects, and then you can select the correction procedure, LSD, Fisher's least significance difference, Bonferroni or Dunn-Sidak. And what this is going to do is it's going to go through and test all possible within subjects comparisons on your repeated measure, right? So if you take a look at our handout that we have for our ordered means. So for this, we are looking at depression scores at time 1, time 2, time 3, and times 4. Baseline 2 weeks, 4 weeks, 6 weeks. Okay. If I go through and as I'm going through and running this, I can go through and ask SPSS to give me pairwise comparisons for time 1 versus 2, time 1 versus 3, time 1 versus 4, 2 by 3, 2 versus 4, and 3 by 4. Just run all those. Basically what this is going to do is this is going to give me paired sample t-tests across all of those repeated assessments, right? Now, reasons that we don't want to do this, if this is just an exploratory situation, right? I've got a repeated measures ANOVA, one-way repeated measures ANOVA, like we ran in these ordered means, right? What this is going to give me is I've got 4 time points. It's going to give me 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, and 3 versus 4. Right? If I select Fisher's LSD, it's just going to give me paired sample t-test for each one of these. Okay, and then if I ask it for Bonferroni or Dunn-Sidak, it's going to give me Bonferroni or a paired sample t-test with a Bonferroni or Dunn-Sidak correction for 1, 2, 3, 4, 5, 6 for 6 different tests. Okay. Reasons we don't want to do this is, one, if I'm a clinical person and I'm looking at treatment of depression over time, assessed at baseline, time 2, or week 2, week 4, and week 6, I could maybe care less whether or not there's a difference between times 2 and times 3. Who cares, right? It's not a relevant situation unless there's something different going on. If there's some aspect of this treatment component that is important to look, we're just asking a bunch of stuff that no one actually cares about, right? And then if I run it, then I have to talk about it and explain why it's important, which is hard if I don't think it is important, right? And so we run a bunch of tests, and Fisher's LSD isn't going to correct for any of that, right? Problem with Bonferroni and Dunn-Sidak is now maybe I'm really just interested in 1 versus 4, but I've gone through and I've corrected for 6. That's a huge penalty to run a bunch of tests that I don't care about and I'm not going to interpret anyway, right? And so wanting to be careful as you now, sometimes there are reasons to do this just in SPSS because it's a shortcut to getting some stuff that you might want to get anyway. But in terms of as an approach to teasing apart omnibus specs within the context of your repeated measures in ANOVA is probably not going to be sort of a helpful thing to do. Yeah. Other thing that you can do with your Tukey correction here, again, SPSS isn't going to give you an option for Tukey, right? But if this was important, if for some reason you needed to compare all possible comparisons between all of these, you need to go through and institute some sort of correction by hand so you know what to compare against, right? And so here we could say what we would do, again, we talked about this last semester, we could create, identify what our critical Q value is, given our table value based on the alpha that we want to use. R is going to be our number of means and our degrees of freedom, right? So remember that R is our number of means. And so in this case, we've got 4 means, right? And so if we set R equal to 4, then that's going to, so the number of tests we're going to compare for is going to be 4 times 4 minus 1 over 2, right? Which is going to give us comparing for 6, right? And so we've got a one-way design, that's fine, because how many tests do we have we gone through and run here? 6, right? Where we start to become concerned is when we're running factorial designs and all possible comparisons aren't interpretable because we cross factors and things like that. But for our one-way, we could certainly do this, right? So what I might do is I might go through and I might say, all right, go to my Tukey table, say alpha 0.05, I've got 4 means, this is going to control for 6 comparisons, and then degrees of freedom error from your ANOVA table, I guess if you wanted to go through and do that, right? And what that's going to do is that's going to give you a critical Q. But remember, your Q critical has a direct relation with your T statistic, right? So we can take that critical Q we get from our Tukey table, divided by the square root of 2, and that's going to give me a critical T value, right? And then what I can do is I can go through and I can run paired sample t-tests for all of these and just compare my test statistic against my critical T that I got from Tukey, right? And now, this isn't going to give you a specific p-value, but with Tukey, at least traditionally, we don't get a traditional T or a traditional p-value. We would just say this is significant Tukey correction at p less than 0.05, right? And so that's how you would go through and run those tests, right? SPSS will give you a p-value for those tests, but technically you're not running t-tests. You're just running those t-tests so you get your test statistic that you then compare against your t-critical, your Tukey t-critical that we got from our Q. Okay, and again, we had talked about this. We talked about this at the end of last semester, how to go through and do this. But questions on sort of how we might hijack Tukey and start to use that if we had some reasonable need to go through and do this stuff. Yeah.
So if we do this in SPSS, we just compare each of the T values they give us, which the comparisons with.
Yeah. I mean, I would just go through and just run 6 paired sample t-tests, right? And then you just look at your test statistic and compare it against to whatever your critical T is that you got from Q. And if your test statistic is bigger than your critical value, you say significant p less than 0.05 based on Tukey correction. Or if you want to be really really stringent, you could derive your critical Q at alpha 0.01 if you wanted to, right? It just kind of depends on sort of what you want to do. Okay. Questions about this? All right. Other thing we can do if we don't want to fool around with Tukey, we can use Benjamini-Hochberg procedure. We talked about this last semester as well. It's kind of taking a different approach to how we're setting up and how we're thinking about family-wise error versus false discovery rates, right? Again, and so it changes up some of the stuff a little bit, right? So with our family-wise error, with our Tukey, we assume that we've made an error and we failed if we even have one type 1 error, right? Benjamini-Hochberg asks, so basically, how many of the effects that I find that are statistically significant are false positives? Because that's what we're worried about, right? We're worried about false positives. We're always worried that we're going to say something's real when it's not. And so what Benjamini-Hochberg does is going to try and say, what's the probability of, or what percentage of these significant effects are false positive, tries to manage that, okay? So a little bit different. What we get instead of one critical value with Benjamini-Hochberg, remember, we have a series of increasingly stringent p-values based on the number of tests that we go through and conduct. So here, your p-critical is going to be the test k is the number of tests. So if you only have one test, your first test would go over 1 times 0.05, so your p-value is going to be 0.05, right? But in this situation where we got 1, 2, 3, 4, 5, 6 tests, right? Your first test, you order them from the smallest test statistic to the largest test statistic. So you'd have, this would be index 6, 5, 4, 3, 2, 1. So this comparison would be if the index number is 6, 6 divided by 6 times alpha, what's my p-value for that one, Haley?
6 divided by 6,
Yeah.
0.05.
Yeah, it's just going to be 0.05. So I'm going to test this at p less than 0.05, right? But this one is going to be 5, so that's going to be 5 divided by 6 times 0.05, right? Haley, you want to tell me what that's going to be?
0.042.
0.042, right? And as we go through and we continue on, as our effects, as our comparisons get larger and larger, we start to get more and more stringent p-values for that, right? So again, for the data that when we go through this, if we wanted to use a Benjamin-Hochberg for these data, right? We see that time 3 versus time 4 has the smallest t-value, 2, 3, the next biggest 2, 4, so on and so forth until we get time 1 versus time 4, or versus time 1 versus time 4. This is our largest test statistic, right? P-value here is all statistically significant because we got tons and tons of people and really massive effects. But what we would do is we would take each one of these tests, right? We've decided that it's important for us to look at all possible pairwise comparisons. So we run all of those and then take our test statistics, we line them up with the smallest test statistic to the largest test statistic, record our p-values, and then we assign each one of these tests an index number where start at the total number of tests we got, and the smallest one gets assigned 6 and then move down, and then our p-critical based on the Benjamin-Hochberg procedure right here. Clearly, we've exceeded, and we would identify all of these as statistically significant, but what we're doing is we're increasing our threshold as we continue and proceed through these different tests. Okay. I like this a lot. This is nice. This is particularly flexible when we're going through and working with factorial designs where it doesn't make sense. All possible comparisons aren't comparable. And so we need to go through and sort of, it can start to become hard to find a Tukey, an R statistic that's going to not overestimate or overcorrect or undercorrect for what you're kind of doing. This is just based on the number of tests that you run and then going from there. So this being a little bit more flexible. All this ringing bells, people kind of remembering some Benjamin-Hochberg stuff. Okay. Cool. So effect sizes. For our specific contrast, this gets a little bit tricky. As always, when we're thinking about effect sizes, our primary concern is what is our standardizer? What do we use as our standardizer? We went through a number of different options with our between subjects effects, but when we get into contrast with our repeated measures designs, we add some new complexities, right? So what Hal advises, has anybody read the Hal chapter? Okay. Again, do this. It's going to be a very, very nice, it's going to reinforce all the stuff that we've gone through and talked about here. I would definitely recommend going through after we finish this up, read through it, take notes. It's just going to make this set a lot easier if you've got a good handle on it. And Hal's going to talk about some stuff that we're not going to get into here, but it's just good background. But what Hal is advised for contrasts is, what do we use as our standardizer if we're running an effect size for a planned contrast, right? So let's say we've got a repeated measures design where we have 4 people measured on 4 occasions, right? So not a much smaller version of our inpatient set, right? And let's say what we want to do is A and B are baseline conditions, C and D are treatment conditions, right? And so our contrast is we're interested in looking at want A and B is greater than C and D, right? And so when we go through, this is gonna, we'll say 1/2 A plus 1/2 B minus 1/2 C minus 1/2 D, right? And this is gonna be the value of my contrast here. Okay. People see kind of the example that we're getting at with this one-way repeated measures ANOVA. So let's say we run this contrast, but then we want to calculate the effect size. Okay. The question becomes, what do we use as our standardizer, right? What Howell advocates, well, I guess I changed this up a little bit. Yeah. Okay, just so let's say we run A and B is greater than D. Minus 1 D. Okay, so we're not including assessment, repeated assessment C in this example, right? So we're saying essentially in this case that people's symptom scores at the final time point will be less than their symptom scores at our initial 2 baseline sessions. Okay. What Howell advocates is, so okay, let's go through and we need to get some sort of standard deviation of baseline. What Howell advocates for is going through and using the standard deviation of the average baseline assessment. All right. So this gets a little tricky. So what he's saying, if you were to be confronted with a contrast of this type, what you would do is take the mean baseline across time points A and B for each participant, right? So we've got for participant 1, we've got A and B, right? So we've got a score of 2, a score of 4. Take the average of that, it's 3, right? So person average of A and B for subject 1 is 3. Average for person 2, 10 and 12. Average of that's going to be 11. Average here, 22 and 29 is 25 and a half. 30 and 31 is 30.5, right? And so then what Howell is suggesting is you take the average score of that person across the 2 baseline assessments and then take the variability or the standard deviation of the average points for that person across this. So what we would do then is take the standard deviation of the combined baseline and use that as your standardizer. Okay, so it's a little bit funky, but it makes some conceptual sense, right? So we've got 2 assessment points, right? So I've got 2 assessment points in that I'm considering baseline. So what I'm going to do is I'm going to take, for each person, I'm going to take their average baseline score, and then I'm going to, in SPSS, right, I would say create average of time 1 and time 2 for everybody. And so it's base average or something like that, and then take the standard deviation of those scores across people, and then use that as my baseline, as my standardizer for my effect size. Okay, and then this is going to be the basic formula, the value of your contrast over some. This isn't standard error. This is so error is some measure of error standard deviation, right? But this is something that Howell proposes would be a possibility for a contrast like this. Okay. Same type of thing if you said that if we included this as C and D, maybe then go through and take the average score at beginning, the average score at the end, then take the standard deviation of that, standard deviation of that to go through and come up with some sort of pooled standard deviation or something along those, our average standard deviation there, right? So you can start to get creative in how you're doing this, but again, the task is what makes the most sense. What if I'm talking about this in terms of an effect size, how do I want to interpret this? So this is X units increase, decrease, or greater or lower relative to standard deviation units of what makes the most sense. Okay. Questions about what Howell's proposing here? Yeah.
So the, like, standardizer is that standard deviation of the baseline? That's what S error is?
Yeah.
Okay.
Standard, S error just being some type of standardizer, some standard deviation estimate of something, of what, then that starts to depend kind of how we go through and do this, okay? Olegnik and Algina is a big sort of classic. You'll see this cited 1,000,001 times, anything having to do with effect size. They offer other options, say the pooled standard deviation of cells including the contrast, right? So here, for this one, we take standard deviation at time A, standard deviation at time B, standard deviation at time D, right? Remembering that the average standard deviation isn't the same thing as the square root of the average variance, right? We want to go through and pool these at each time point, right? So in this scenario, we would go pooled would be n-1 variance of A plus n-1 variance of B plus n-1 variance of D over n plus n minus 3. Just to make sure that that turns out. I mean, you've got the same people in each one, right? So technically, this is going to cancel out. And if you're sort of recognize the mathematical equivalence, you would just take the average variances across these and then take the square root of that. But this is just what it would look like in a pooled format. So I mean, because we've got a repeated measures design and we've got the same number of people in each one, right? In this case, this is going to be the same thing, right? But just wanting you to be aware of how we could use that pooled variance estimate, or that pooled variance formula to go through and make sure that we're addressing this. Again, with our repeated measures designs, because it's the same people each time, sort of the pooling thing, we don't really have to worry about weights. And so if you know that, you move back and forth, that's fine. What we don't want to do if we have unbalanced designs, different number of people in each cells, just taking the sort of the raw average, because someone's going to get more weights than others, okay? And so then just using this, and then take the square root of this to then go through and use that as our standardizer. Other thing you could do, you could take pooled standard deviation of all the cells in the design, right? That's kind of just your overall standard deviation, right? So you take the variance at time A, variance at B, variance at C, variance at D, you plug it into a pooled formula, or literally you can just take those 4 variances and average them, and then take the square root of that, right? If you wanted to, because again, maybe we have, like in our unordered means, where we have, there's no relation between all of these, right? These could be very different measurements in response to very different scenarios, right? And so maybe taking the pooled standard deviation of everything doesn't make any sense. What we want to do is just look at the pooled standard deviation of the cells that are involved in the contrast. Or maybe we just want to say, hey, we want to get sort of total variability in here, and taking sort of the pooled variance of each one of these really kind of depends. This is a conceptual question you want to think carefully about in terms of how you're going to go through and standardize your effects here. Questions about some of these options? It starts to get tricky when we've got multiple repeated assessments and how we're going to go about doing this. Yeah.
So I guess for these 3 options, how do you know which ones to test?
Again, that's the justification you need to come up with, right? And again, it's going to depend on your question, on your data, about the design characteristics of the study, right? If you've got pretty consistent variability across these, it's all pretty much the same, probably doesn't matter a whole lot. It'll make an incremental difference, right? Depending on which one you use, it's always going to change your effect size to some extent. What you don't want to do is make sure that you're not making your determination on what effect size metric you use or what you use standardizer based on what gives you the highest effect size, right? So what you want to do is you want to think, okay, so I want to compare these two conditions to this condition. What makes the most sense in terms of my standardizer, right? Now, if they're all about the same, it probably doesn't make too much of a difference. But if you've got wide variability, then maybe it does start to make a difference, right? It really kind of depends on what the question is and what's going to make the most sense in terms of interpretability. Because again, these effect sizes, hopefully what you get out of this class is not just using effect sizes as sort of a number that you compare against Cohen's benchmarks and edema, high, medium, or low. Hopefully what you're thinking about is using this as a real way to start to quantify the magnitude in some meaningful metric, what's going on with this stuff.
So if you had multiple baselines, let's say, in comparison, it's going to make more sense to use hours.
Yeah, maybe, right? So if you're doing, say, a stimulant trial on kids, right? You've got sort of day 1, day 2, day 3, no medication, and then medication on day 4, day 5, and day 6. How kind of sounds good, right? Because if I want to say, here's my baseline, and then here's not, so it's starting to combine some of that stuff, right? You know, the thing that he's doing differently is saying maybe time 1, 2, and 3 are all baseline, right? And then time D is your medication, right? Maybe what you do is then take the average of your 3 baseline scores and have a number for that, average of these, average of these, average of these, and then take the standard deviation, your average baseline, right? That would probably make a lot of sense. Say on average, right? Particularly if these are all baseline conditions, people shouldn't be moving around too much. Hopefully we've got some stable sample of behavior, right? Cool, let's just do that, right? But if we've got a situation where, you know, these are all like very, very separate types of conditions, then maybe allegenic and alginous stuff sort of makes more sense. Right? And this is the test. This is really where it's really hard, right? This is where you become frustrated as we move forward. People like, oh, you have to do this, and this is the only way you can use your standardized. And you're like, nope, I could. That's one way. That's an option. But this is why I've chosen to do this, because within the context of my study, it makes sense. It increases interpretability. So just because you saw it somewhere in a website or in a stat class doesn't mean that that's the only way to go about doing stuff. Okay? So with this stuff, I'll help you in the assignment. I'll kind of tell you, point you in the right direction on things that I think are going to be appropriate. But once you get into your own studies, you want to think carefully about sort of what makes the most sense. Feeling good about this? All right. Cool. Repeated measures, confidence intervals on repeated measures effects. This is where we start to get into the wild, but like literally, the literature is continuing to develop on the calculation of effect sizes for repeated measure designs. As their computing starts to get more and more increasingly sophisticated, right? This is something that Ben runs into with some of his EMA studies. You know, the social journals are wanting to give him an effect size for these EMA designs, and he's trying to explain literally there are no effect sizes. Like there's nothing that's useful and meaningful that anybody's yet developed. And sometimes they say, well, we want one anyway, and so then it's just, I guess my effect size is 4. If you don't care if it actually means anything, right? But for right now, for our repeated measures, for eta squared, omega, partial eta squared, partial omega squared, for our repeated measures design, doesn't look like no one has a good way of calculating, at least from what I've been able to find, confidence intervals around these omnibus tests for repeated measures effects. We have guidelines for between subjects effects. Those are different and not to be used for within subjects effects. And so that gets a little bit sticky. For our paired sample tests and our contrast, we could probably store any type of confidence interval around any type of effect size. Because we're getting that interval estimate, that upper and lower limit from a test statistic that we're plugging into our Steiger calculator here, right? And then we get an upper and lower bound for a non-centrality parameter. What we want to do is make sure that the point estimate for our effect is based on the same variance estimate as we're using in the calculation of our test statistic. Because if we start to cross that, particularly for repeated measure designs, things start to get tricky. Okay, what we get for repeated measures tested, I've got an upper and lower bound for an effect size and a point estimate that doesn't fall in that confidence interval, which is clearly problematic, right? So again, as we talked about before, for our paired sample t-test, what we want to do is use the standard deviation of the difference score as our standardizer. The standard deviation of difference score is what goes into calculating the standard error of our test statistic. And so if I am running a repeated measures design and I'm wanting to provide confidence intervals around effect sizes for pairwise, for my paired sample t-test, if I want to create confidence intervals around that effect size, that all of a sudden gives me only one option for the standardizer I'm using in that, right? I just have to use the standard deviation of the difference score as my effect, as my standardizer in that situation. Remember that we have talked about some problems with using the standard deviation of the difference score as our standardizer. One, from an interpretive standpoint, so we're saying, well, there's a group 2 or scores at time 2 where a half a standard deviation in terms of standard deviation of difference, it starts to get kind of circular, right? If we're using like glasses delta, I can say scores at time 2 were a half a standard deviation above scores at time 1 based on variability, relative to variability at baseline. That makes some sense, right? We lose some of that if we're using standard deviation of the difference scores. So based on, we've got a half a standard deviation increase based on variability and difference across change. We could do it. It starts to get kind of bulky though, right? Other concern, remember with our repeated measures designs, is that the standard deviation of the difference score can be quite a bit smaller than the standard deviation of scores at time 1, time 2, things along those lines, right? We could have wide variability in where people start and where they finish, but if everybody changes about the same, right? Standard deviation of my difference score, scores at baseline range from 15 to 95, and scores at discharge range from 30 to 140. But if everybody changes, so everybody's change score is about 10 points plus or minus, right? Standard deviation by difference score is going to be much, much smaller than variability at time 1 and time 2. And so there's concerns about using standard deviation of the difference score, potential for that to inflate your effect size, right? And so you probably should look at this, if you're thinking about using standard deviation of the difference score, compare it against a glasses delta, something like that, or a pool, using a pooled standardizer, just to see, is my effect substantially larger than sort of what I would expect with some of these other metrics? And if it is, then you want to be careful about sort of how you present that stuff. But you all have wonderful Excel calculators. You just punch mean standard deviations and cell sizes and stuff like that. It's going to give you all sorts of different effect sizes. You can just look at that and say, okay. And oftentimes what happens, particularly again for clinical folks, if you're using standard deviation of the difference scores for like pre-post stuff, just because everybody, particularly for treatment stuff, people can be kind of all over the board and whether or not they responded or not. Sometimes standard deviation of the difference score is actually quite a bit larger than standard deviation at baseline or post, right? So this isn't always a thing, but it's something to be aware of that you want to make sure that you address. Questions about this? Okay, cool. Let's jump back in to our example where we were using our not our belief rating set, but the ordered mean set. Grab your handouts here for your one-way repeated measures ANOVA. Remember what we had gone through and we had done. I'm missing data here. No. Okay. So, if we go and we're just going to go through and run our one-way repeated measures ANOVA here. So if we go to analyze, and we did this last time, go to general linear model, repeated measures. We've got our factor is time, 4 levels to time, add that, then hit define. We've got time 1, 2, 3, and 4. Okay. And then model, we can ignore this. You can get fancy with your sum of squares and things like that, but you probably won't need to change that unless you have a strong reason to. Contrast, remember that these are ordered means, and so it's going to give us polynomial contrast, which we, in this case, we can go through and interpret. So we're going to go through and keep that. Plots, we'll plot time on the horizontal axis here. Again, SPSS's plots are really no good, but it'll at least give you kind of a sense for what's going on. Post hoc, we don't have any between subject stuff, so there's nothing to put in here in terms of post hoc. We'll talk about that when we get into our mixed designs. Save, here you can go through and start to save some different statistics based on your model stuff. We're not going to worry about this for your repeated measure designs. But then we go down to options. Okay, what we can do is we go down, we can set descriptive statistics, estimates of effect size. We could test homogeneity variance. What will that do if we click homogeneity variance test? It'll tell us no, right? Because SPSS is only testing homogeneity variance between subjects stuff. So it won't give us, because this is a one-way repeated measure, there's no there's no between subjects factors. But what we do is we have our time factor, right? This is our repeated measure. This is a time 1, time 2, time 3, times 4. What we can do is if you go down through, you can compare main effects. Okay, this is what I told you not to do, but we're going to do it anyway, just so you kind of see what's going on. And I can choose a von Fermi correction, Dunn-Sidak correction, or Fisher's LSD. There's no correction. What this is going to do is it's going to give us all of these comparisons here, right? SPSS will run them for you, and it's a quick way to get them if you're interested in looking at them. But as in terms of an approach or something to do, not something that you want to do as part of your formal stuff. But we'll do it on black arts and stuff like that. Okay. All right. Gonna hit OK. And this is all stuff that we've seen before. We can go through and always want to go through, make sure you're within subjects factors, map on your descriptive statistics, go through and make sure that that looks all reasonable. Hopefully before you run this, you've gone through and screened, but again, what I always do is I have like a 999 code that I forget to tell SPSS means it's missing data, and then I've got something wacky, right? So wanting to make sure all those means are plausible. Make sure that you still have the number of people that you think you should have in here. Ignoring, so one thing we can do here is think about calculating F max, right? You can do that. Again, we'll have probably done that already in your screening stuff. But remember, F max is going to be your highest variance to your lowest variance. And so if we look at our standard deviation, we've got the greatest degree of variability at intake, so 12.688. What's the, Laura, can you calculate variance for that? So just square that and tell me what that number is. For time 1. So square the standard deviation. Yeah.
160.985.
And then our least variability is at 6 weeks, that's 9.551. What's the square of that? What is it?
91.222.
91.222, right? And if we divide those, what do we get? 1.76. Okay. So F max here is 1.76. That's probably all right, right? We talked about for our between subjects designs, if we get F max of like 3 with a largely unbalanced design, then we start to have some concerns about sort of problematic variability or differences in our variances across groups. With our one-way repeater measures ANOVA, we can't have unbalanced designs. It's all going to be the same number of people in each one, so we have a little bit more tolerance here. 1.76, I'm not too worried about this, right? So our sort of the ratio of our largest to our smallest, and our smallest, 1.76. If they're identical, it'd be 1, right? So we're doing pretty good in terms of this stuff, right? This starts to get more complicated when we get into mixed factorial designs, because we're going to have within subjects factors, we're going to have between subjects factors, and we're going to have to figure out exactly how to go through and take a look at that, because SPSS isn't going to do it for us. Okay. So we've gone through, we've done that, and we are ignoring our multivariate tests. Note our test of sphericity. Do we pay much attention to this, Layla? No? Why not? Yeah, we would assume we violated it anyway, so we really don't actually care what the sphericity test says. If you were going to say, oh, hey, we didn't violate sphericity on this repeated measures design, you're going to have to come up with a pretty good, strong evidence that sort of for why you're not using corrected statistics. So we're going to go through, note that, and then just go down through and take a direct look at our test of within subjects effects. Okay. Evelina, what are we seeing here in terms of our within subjects effects?
Reliable variance after pulling down some of the individual.
Yep, yep. So we, based on this, we can take a look, and that's pretty large, right? So we're saying based on these data, based on the results of our analyses, suggesting that there is statistically reliable variability in mean assessments over the course of time, right? Suggesting at least one of these assessment points is different than at least one other assessment point across my repeated measures, right? And so I'm getting that in my within subjects effects. Down here, my between subjects effects, we just have an F test for our intercept, which just basically says that we have different people are scoring differently on their measures overall, right? Which is what we would expect anyway, right? If this wasn't statistically significant, it would mean pretty much everybody is scoring the same at time 1 and the same at time 2 and the same at time 3. That would be a weird thing, right? So I want you to understand what this is about, right? Remember when we were sectioning off variability, this is where all between subject stuff goes. This is the individual difference and stuff, right? And the more of this there is, the more powerful your test is, right? Because there's more variability across your assessment points, probably means that you're gonna have stronger correlations across your time points, and the correlation across your repeated measures is what's the biggest driver of your power with these designs. So just kind of knowing what this is about. But if we go down through and then we take a look at our marginal means will be identical to our observed means. But we go through and we take a look at our repeated measure. This is what this looks like, right? We just see very clear treatment effects where people start here with their depression scores. At week 6, they're down at the bottom of their depression scores. We've got, I can look at this, I have a pretty good sense of what's going on in terms of this omnibus test, right? But a couple of different things we can go through if we want to provide a formal assessment of this. If we go back up, right, we had talked about our within subjects contrasts right here, right? What this is doing is it's providing a test, and this is something that you can look at if you have data that has some meaningful order to it. What it's going to do is it's going to provide a test of a linear trend, a quadratic trend, and a cubic trend for these data. Okay. So if and the number of terms that it will test out here is going to be based on the number of data points that you have. So you've got 4 data points or 4 repeated assessments, and so it will give you up to your third order polynomial here, a cubic function, right? If you had 3 data points, it would score up to a quadratic. If you had 3, or excuse me, yeah. If you have 4, it'll give you a cubic. If you have 3, it'll give you a quadratic. If you have 2, it'll give you a linear, although that's not super helpful for much of anything. But what we're seeing here is that these data have a significant linear trend, right? And if we look at that linear trend, what it is, it's suggesting that yes, these data are following there's a significant linear reduction in these means over the course of assessment, right? Which for these data might be interesting to go through. This just gives you a formal test. These are just like any of our other contrasts that we use. SPSS is just doing it for us, and the weights are a little bit different on this. So this being significant, and because we can interpret this because we have data that are following a systematic order, we can say that we have an omnibus effect suggesting that there is variability across assessment, across our repeated measures, and specifically our linear trend suggests that we've got a significant linear trend indicating reductions in symptoms over time, right? And you see your partial A squared quite large for this, so you've got a massive linear trend going on. You can also go down through and you see a quadratic trend here. Okay? Can someone tell me what a quadratic trend looks like? Yeah, it's like a U or an upside. It's a parabola, right? Which is the first sort of our first indicator of a nonlinear trend. Now, for these types of data, right, a quadratic is technically this or this. It's x squared, right? What often will get you a quadratic trend in some data with some orders, if you have rapid increase that sort of tapers off, right? That would be a nice, I mean, it doesn't catch the full thing and start to come back up, but for the scope of these data, it's catching this curvilinear trend. We get the most improvements at the beginning of, at the early points of assessment, and as we continue on, that assessment, the change starts to decrease as things move over. Anybody here calculus? Anybody take calculus? Took calculus?
Yeah.
Long time ago, right? Yeah. But, Kate, did you take calculus?
Yeah, but.
Don't, this is lying by omission, right? I'm not going to ask you to go through and do proofs, right? But the idea, if you think about, remember back to calculus, right? A lot of what you're doing is looking at change in a function at some time point, right? Like talking about tangent lines, right? So like immediate change at time 1, at time 2, at time 3, right? Seeing the rate of change decreasing as we go across time, right? And so quadratic could be something that you could reasonably interpret. It's statistically significant here. And if we go down through and we take a look at our means, I can see where that quadratic trend is coming from, right? It's not a straight line. It looks as though over the course of time, so there's a trend to that. Like the changes over time are starting to even out, which is consistent phenomenologically with what we often see with treatment, right? Early on, big rapid change, and then as we continue on, you're getting better, kind of sort of plateau out. Okay. So we could say also report on this quadratic trend, saying that there's also a quadratic trend was significant with sort of strong interpretation with these types of designs is a little bit tricky. It's easier if you've got like a growth model or something along those lines, but you can interpret that as suggesting quadratic trend, suggesting most rapid decreases at the beginning and then kind of tapering out over the course of later assessments. Now, you also have a significant cubic effect, okay? Cubic effect is executed. All of a sudden, we start to have a harder time figuring out whether or not this makes sense, given our data. Now for these types of effects, what you might find is if you had data that kind of did something like that, that might be consistent with the cubic effect, right? So we have initial rapid gains and then things kind of plateau or sort of stay stable and then they go down a little bit, right? SPSS will give you polynomial transfers many, they'll continue. So if I had 5 assessment points, it would give me a test of the 4th order polynomial here, right? If I had 8, it'd give me a test of it all the way up to a 7th order polynomial. Just because something gives you a test doesn't mean you're obliged to interpret it or make anything of it. Remember, we've got how many people in this set? 388. I don't know. One, I don't know where the cubic trend here is coming from. I don't know how I would interpret that, even if it was there, right? And so wanting to be careful and not just report p-values based on what's statistically significant within these data. Always, always, always remember that anything that you're going to interpret, you need to be able to come up with some plausible reasons for why that's important and why this isn't just capturing sample-specific stuff going on in this set. Okay. So, questions about our within subjects contrast or polynomial contrast. So this is our trend analyses. Okay. So this is one way we could go about it. Or another thing we could do. If I'm looking at these data, right, and I find that I have a significant within subjects effect here, indicating that my means are demonstrating variability over the course of repeated assessment. What's maybe a simple follow-up that I might want to ask about these data? Yeah, pre-post, right? And this is the thing where if I go through and I take a look at my means, right? I'm going from a mean of 26 down to a mean of 8 with 233 people. Do I really need to run a statistical test to see whether or not this is statistically reliable? No, right? I know it's going to be statistically significant, right? I know that I'm going to have a significant change from pre to post treatment, right? But what might I also want to do? So yeah, it's statistically significant, right? The mean of the difference scores from time 1 at baseline in week 6 are not 0, right? Is that useful information? No, not really. What might be more useful information? How much, right? How much a difference, right? So what I might do is I might go through and I say, okay, I'm going to go through, and the way I'm going to follow up with this, it's very clear what's going on with these data, right? Do I need to compare whether or not people at baseline in time 3 is different or time 2 and time 3 is different? Probably not, right? So what I'm going to do is I'm going to go say, okay, I'm going to go compare means, paired sample t-test. I'm just going to take a look at baseline to 6 weeks. Okay, I'm just going to request a paired sample t-test, just looking at person and intake and finish. Right. And I'm going to run this. I'm not going to run it necessarily because I want to see if that's statistically significant. It clearly is. Right. It's clearly significant. Right. That's not the point. But what I do get, what might I get out of this paired sample? Running this paired sample test that might be useful to interpret. What do you think, Kate?
The confidence interval?
Absolutely, right? Because if I'm wanting to see, you know, whether or not this is a treatment, or whether or not it's some sort of experimental paradigm, some sort of manipulation or something like that, what I might be interested in saying is, okay, not just like, do people change? How much do people change, right? And how much, if this is a good study, right, and I've got 388 people in this, right? If I'm going to tell somebody else, if you have somebody come through and participate in this program, how much should you expect on average people to change? And here, right, we see that your mean of your difference score is close to 18 points, right? So what I'm saying is, on average, I'm expecting people symptoms to reduce by about 18 points, based on the data that we've got, reasonable plausible estimates for the population change, somewhere going from 16.5 to 19 points. Now all of a sudden, that's interesting information, right? Not that, yeah, it's statistically significant, right? Change in this treatment program is not 0. Well, fine, right? But if I know what this scale means, if I'm familiar with this measure, and if you use the Beck depression inventory, 18-point drop, that's pretty good, right? And on average, people were expecting people to change anywhere from 16.5 to 19 points. That's pretty good, right? And so this starts to become more interesting ways of using our point estimates and our confidence intervals to start to, and then if I give you these, this confidence interval, 16.5 to 19, do I need to run the paired sample test? What do you think, John? Like, well, I ran it just so SPSS calculated it for me. But if I give that interval estimate, do I have to provide my paired sample t-test if I'm reporting this? No, right? What if someone says, well, is that a statistically significant difference? What do you say?
You could say,
Well, yes, it's a statistically significant difference because it doesn't include 0, right? 0 is not even in the ballpark of a reasonable change score in any of this, right? And so using this as a way, you know, if you were to do this and review it back, oh, well, you need to run a formal statistical test back at the confidence interval. Right? Does that contain 0? Then it's p less than 0.05, so calm down. There's more important stuff to be focusing on in terms of magnitude of change. And, you know, clinical stuff is a nice example of sort of an application of this, but even if you're talking about, you know, other type of applied stuff or experimental types of designs, you know, sort of this point estimate, the effect size for the magnitude of a manipulation, still at the end of the day is going to be communicate more information than a p-value that, yes, it changed by some non-zero value, right? So wanting to think about this. So going through confidence interval is a nice way to go through and present this information. What we also might do is calculate some effect sizes, right? So if I were to go through and calculate a pooled variance estimate here, right? If I go through and I take a look at my means and standard deviations earlier back, and because this is a repeated measures design, right? I'm looking at people at baseline and people at 6 weeks. It's all the same people, right? So I can start to reduce my pool down. And if I take my variance at baseline, take that standard deviation squared, I'm going to get 160.985. That's my variance, plus my variance at the final time point, give me 9.222. Take that, divide that by 2, right? It's going to give me a pooled variance estimate, 126.103, which again will give me pooled standard deviation. I take the square root of that, 11.230. You'll see how I got that.
Did you mean 91.222?
Oh, yep, 90, excuse me, thank you. 91.222. we see sort of how I went through and did this. So basically what I'm doing, I'm just getting my standardizer, right? I'm taking, so this is just one way I could go through and calculate this, right? And so if I were to calculate what we'd called last semester the average, right? This is going to be taking my, at my sort of final time point, score is 8.65 minus 26.44. Okay, that divided by my average of my squared variance, right, is going to be 11.230. It's going to give me an effect of 1.58. Okay, but maybe I want to see how that compares to if I want to just use the standard deviation of baseline, right? Maybe I want to calculate Glass's delta, right? So then I can go through and just pull sort of mean difference from my test here. So that's going to be negative 17.791 over standard deviation at baseline is going to be 12.688. Going to give me 1.40. Right. And so a little bit different, right? Here I'm saying that I'm getting over a standard 1.5 standard deviation decrease in symptoms based on variability at time 1 and time 2, right? Here with Glass's delta, I'm saying I'm getting 1.4 standard deviation decrease in symptoms based on standard deviation at baseline, right? So just my standardizer starts to influence how I want to go through and talk about that. If I want to use what we're calling D difference, right? So this is using standard deviation of the difference score. Standard deviation of the difference score is 12.668, right? So I go negative 17.791 over 12.668. I'm back at 1.40. I don't know. This is a weird coincidence. Standard deviation of the difference scores is identical to the standard deviation at baseline. That shouldn't happen. That's a lottery ticket thing there. Just don't get confused about what that's going on, right? So the standard deviation of the difference score, I'm literally taking, or excuse me, they're not the same. This is 12.688 and this is 12.668. They're not the same thing, so just mark that in your notes so later on you don't look at it and get confused, right? But here, so I end up with the same effect size as when I use based on my Glass's delta, right? And so this is nice too, because then what can I do? What can I do with this that I can't do with these two? What do you think, Evelina? What can I do with this effect size that I can't do with these other two?
Compare against other effects?
Not quite.
Confidence.
I can create a confidence interval around this, right? Because my standardizer here, this is the same variance estimate that goes into calculating my test statistic, and the test statistic is what I need to get the upper and lower bounds, right? And so for this, remember, this is where we would go through and take your test statistic of 12.664 with your degrees of freedom, put that in your Psyc calculator, get upper and lower bounds for your non-centrality parameter. And if I go through and look at this, I get lower bound of 1.26 to 1.54. Okay. So this is nice, because I can say we're expecting approximately 1.4 standard deviation decrease in symptoms from baseline to 6 weeks with population estimates ranging from 1.26 to 1.54 standard deviation reduction and stuff, right? And now all of a sudden this starts to become really interesting and meaningful, right? Because we can say, not only we can provide confidence interval around sort of the actual mean difference, provide confidence interval around our effect size, and we say, hey, even when we're looking at standardized effect, lower bound estimate of my effect size for this is still massive, massive, right? Suggesting that we've got a pretty good program here. Looks like this is pretty effective on average for people. Okay. So with this type of set, given my questions and things that might be interesting, I don't need to go through and do a bunch of pairwise comparisons between all possible time points, because it's not useful or interesting, right? Unless you've got there's something going on kind of in the center of this that you want to tease apart. But for the most part, if it's just saying, is this a good program? Outcomes look pretty good here. Right? So again, we just want you to be thoughtful and think about how we're going about approaching and teasing some of these designs apart. Okay. Questions about any of this stuff? Okay, cool. Let's go through, take a break. When we come back, we'll jump into unordered means, and then roll into our factorial designs. The ordered means. I'm kind of okay with that? Okay. Let's go through and pull up your beliefs rating set. Okay. Remember what we had here is participants going through and rating their willingness to provide friendship to individuals in a series of 8 different vignettes. Okay, this one here, repeated measures, belief ratings. So if we go through, and again, we went through this last time. We go analyze, general linear model, repeated measures. We call this vignette. Got 8 different vignettes, so the big design here. Hit define. What we're going to do is I'm going to put motor vehicle accident stuff first, MVA stuff first, then combat, and I'm going to drop down and put in assault. I'm going to stack up our trauma related stuff, and then disaster disaster fourth, and then finish with infidelity, chronic illness, job relocation, and finance stuff at the end. Okay, so again, what we've done, 8 different vignettes for these related trauma-related experiences, for stressful but non-trauma, the things we often typically think of as non-traumatic. Not going to fool with model, not going to mess around with contrast. Plots, we'll go through and plot vignettes on a horizontal axis here. Post hoc stuff, again, we don't have any between subjects factors, so there's nothing to post hoc. Nothing to save. Options, descriptive statistics, estimates of effect size. Again, we don't have to worry about homogeneity, homogeneity tests. We could put display marginal means for vignette. Those are just going to be the same thing as our observed means. And again, we could compare effects. And again, we could choose LSD. And what this is going to do is now this is just going to run all possible pairwise comparisons between all 8 of those vignettes. And that's a lot, right? If we've got 8 vignettes, 2 is, whoops, 8 minus 1 is 56. It's 56 divided by 2.
28.
28, there we
I
go.
did that in my head.
Good work. 28 pairwise comparisons, right? Is it responsible to run 28 pairwise comparisons? Who wants to try and sort of interpret 28 pairwise comparisons? Doesn't make any sense. But we'll do it just because, so you can go through and see what's going to go on there. So we'll go through and hit continue, and we're going to hit OK. All right. So again, up top, we have our vignettes, car accident, combat, sexual assault, and disaster. And then we have infidelity, illness, job, and monetary lose your finances stuff. Again, remember that when we're looking at our descriptive statistics and our mean level, our meaning ratings of friendship, and again, this is a 0 to 8 scale. Screw that guy to absolutely I'll be there and provide support for them no matter what, right? 0 to 8 scale, we're looking at these means. There's not a lot of variability there, right? Everything looks pretty close to one another. So we might be concerned about whether or not we're going to detect any differences, but we've got a really massive sample, right? And remember that these are very, very powerful designs. And so a little hope here, ignore the multivariate test, take a look at our sphericity, obviously violated, but we're going to proceed to our corrected tests. So we go through, look at greenhouse geyser for tests of within subjects effects. We're very clearly seeing statistically significant variability in the means across these repeated assessments. So this is good, but we've got 8 different means, so I don't know exactly what's happening, where that's going on, and so on and so forth, right? So again, notice here, within subjects contrasts, we've got all sorts of stuff going on here. Can we interpret these? Why not, Haley?
Because they're not, the order doesn't matter.
The order doesn't matter. The order is arbitrary, right? I could go and mix these up any way I wanted to, right? This is looking at polynomial trends over the course of repeated assessments. So there's a lot of statistically significant stuff in there, but it doesn't, there's nothing there to interpret, right? Also notice that we've got a six order polynomial that's very clearly statistically significant. Does that mean anything? A 6-order polynomial, they have 5 humps in it, right? So again, just being careful that just because something's statistically significant doesn't mean it's meaningful or worth interpreting, particularly here because we don't have any type of ordered means. So if we go down here, these are marginal means, which are going to be the same as our observed means. With this, here are all of our possible pairwise comparisons across all things, right? This is not a useful thing, right? This is running 28 unique pairwise comparisons. There's a lot of overlap and things like that, but that can be a useful thing for a quick way to get paired sample t-tests out of this, but you want to be careful. And then if you just run the paired sample t, it's going to give you confidence intervals. Does this give you confidence intervals? Yeah, it does give you confidence intervals. This would be a quick way to run through and grab some stuff, but not an approach to interpreting much of anything, right? And so we see maybe here where we got that 6-order polynomial because things are kind of jumping all around, but the order that we put these in are arbitrary, right? So what we want to do is we want to say, okay, how do we go through and make some sense of this? What might be a reasonable way to proceed in terms of sort of testing what's going on? So again, our omnibus effect says that there's variability in our friendship scores across repeated assessments, right? All that's just saying is at least one of these points is different than at least one other point, right? But what we want to do is come up with a reasonable theory-based or interesting way, question to ask for how we might go about to make an interpretation based on this stuff. So we talked about it last time. What might we want? What test might we want to run in these data?
Just a contrast.
Contrast of what?
The traumatic versus.
Yeah, I mean, I think I would be interested in that, right? Are people more or less willing to provide friendship and support to people, to hypothetical of survivors of traumatic trauma or stressful but non-traumatic events, right? And so what we can do is we might say, I want to go through, and remember that I ordered these, so my first 4 data points are trauma-related vignettes, the last 4 non-trauma-related vignettes, right? So what I might do is I might say for my coefficients, say I want to contrast the first 4 and the last 4. Or what are my coefficients going to be for this contrast?
I'm not sure with the signs, but let's go with positive 1/4, positive 1/4, positive 1/4.
Yep.
And negative 1/4.
Yep. So 1/4, 1/4, 1/4, 1/4, minus 1/4, minus 1/4, minus 1/4, minus 1/4, right? Now, will SPSS do this for us? No, it won't, right? So if I want to, I'm gonna have to do this by hand, right? So the value of my contrast here, I'm gonna shortcut this using algebra. I'm just gonna write 1/4, right? Times, so this is just my mean score, so we use 7.645 plus 7.338 plus 7.654 plus 7.636, right? Those are my trauma people, right? Minus, because my hypothesis maybe here is that people will be more willing to provide support to people exposed to trauma than sort of stressful but non-traumatic events. So minus 1/4 times 7.152 plus 7.615 plus 7.134 plus 7.359. Okay. This is just the value of my contrast, yeah.
I have a question. I think it might be really, really dumb.
No, what's up?
I'll ask it anyway. So in this case, in this situation, could you average the means from trauma and non-trauma and then assign it like 1/2 and negative 1/2, would that achieve the same thing?
Mathematically, it would.
Okay.
Okay. You're catching the pattern here, right? What you want to do, though, I mean, basically, functionally, what are we doing in this? And you've kind of got it. What are we doing with this contrast here?
You're just averaging the two
Yeah,
things.
we're just taking the average of our trauma ratings, comparing them against the average of our non-trauma ratings. So in order to get the value of your contrast, if you understand that that's what you're doing, if you wanted to shortcut it, you could, right? Now the issue is we do need the specific value of those weights, because those are going to start to go into calculating your standard error. So you do need those, right? But you're absolutely right. Conceptually, all we're doing is we're just taking the average of the first 4 and we're subtracting the average of the second 4. Conceptually, that's exactly what you're doing. Okay. Other questions on this? Okay. So if we go through, value of our contrast here is going to be 7.571 minus 7.315. Give us value of our contrast of 0.256. Okay. How do I feel about that difference score? That's kind of what I think too, right? Right? That's not a huge difference, right? But remember that we do have an incredibly powerful design. We've got a lot of people in this study, and also, if we think back to what we're actually doing, we're pulling for null effects, right? Because basically we're giving people a vignette about a hypothetical survivor of something bad happening and asking people, would you be willing to help that person, right? There's a strong social desirability bias going into how people are responding to this, right? So if we do find an effect, I'm going to be kind of impressed, right? Because we're fighting against social desirability in this type of thing. If we, and sort of working at the high end of the scale, if we do find an effect, even if it's small, kind of impressive, right? So what we're going to do, remember that for our contrasts, or for our tests, for our within subject contrast, our test statistic is going to be value of our contrast over the sum of our individual weights squared times mean squared error from your ANOVA table over the number of people in each one of your cells, which is the same number of people each time, right? So if we go over here and I say my test statistic is going to be value of my contrast 0.256 over square root. I'm going to take a shortcut here because all my weights are the same. One doesn't matter if it's plus or minus 1/4 squared, right? So I'm just going to go 0.25 squared times 8, right? You see what I did there? Just took some shortcuts. I mean, because essentially it's 1/4 squared plus 1/4 squared plus 1/4 squared plus 1/4 squared plus negative 1/4 squared, negative 1/4 squared, negative 1/4 squared, negative 1/4 squared. Mathematically, it's just 1/4 is 0.25. You just square that and multiply whatever that is by 8. So it essentially gets us at the same thing. So I'm running a shortcut here, but people see how this is functionally equivalent to that up there. Okay, cool. And then we're going to take that times mean squared error from our ANOVA table, right? So if we go back through and take a look at mean squared error for your greenhouse geyser correction from your tested within subjects effects, what's our mean squared error here? Mean squared error from your tested within subjects effects for the greenhouse geyser.
0.766.
0.766. Okay. Did you get that, Leila? Did you see what?
Maybe I did something wrong.
Okay. It'll be correct in your handout. 0.766, right? Over, now this is tricky. How many people do we have in each cell?
$231.
231. So this functionally ends up being, for our one-way design, just how many people you have in your design, right? So if we do this, we get a test statistic. So we get 0.256 over 0.041 gives us a test statistic of 6.29. The 6.29 is going to be statistically significant. Yeah, it's going to be highly significant, right? And so technically, what's the degrees of freedom we would test against for our critical value here? What do you think, Evelina? You got it?
231 minus 8.
What's that?
Right, is it 231 minus 8?
Okay. Where are we pulling our degrees of, what's the degrees of freedom associated with in this? What's that?
Error?
Yeah. And so how many degrees of freedom was associated with our mean squared error that we pulled out of our ANOVA table here?
1,177.
Yeah. So technically, right, degrees of freedom for this test, 1177. Okay, and so once again, this is, we got a billion people, like it's rare. I mean, I set this up to be a repeat because I was worried about sort of ability to detect some pretty subtle effects, right? So did this online, got a big sample to be able to detect some of these effects, right? And so again, you can start to see how, if we're going through and we're running sort of a classic approach where we're pulling terms from your overall ANOVA table, so where you're getting additional power. Now, with a test statistic of 6.29 for a t-test, that's obviously going to be statistically significant no matter what your degrees of freedom are. But this isn't always going to be the case. Sometimes you're going to get effects that are even more subtle than this with less people. So, but just want to make sure that you're sort of getting things correct in this. Okay. So then we can go through We could run effect sizes. We could get our pooled standard deviation, or actually for this, it's just the average of the variance at time 1, time 2, time 3 across the whole thing, right? Run an effect size for it, same thing as we did before, right? But here we could say, based on these analyses, right, that our omnibus one-way test indicates variability. There's significant variability in ratings in mean friendship ratings across a vignette, right? And we get that from our omnibus. But then what we can do is lots of different ways to go through and tease this apart. We could say, based on our contrast that we've ran, that it does appear that people tend to rate individuals, report being more willing to provide friendship and support to survivors of traumatic versus stressful and non-traumatic events. Okay. Now, does this contrast get at everything that's going on in these means? No, there's some other stuff going on in there, right? But we'll tease out some of that stuff when we get into some factorial design stuff. All right. Questions on this?
Did you purposefully pull 231 people in each cell?
Think about that.
There's your dumb question that you were asking.
No. Yeah, it's a repeated measures design,
Gotcha.
right? So we got the full sample reporting across all of these, right? But this,
Oh, wait, I get it.
but this is, I mean, with this study, I did this on purpose because, again, if I were to run this as a between subjects design, even if I had 231 people in each cell, which would be, what did I take? 231 times 8. I have 1,848 people in this design if I run it as a between cells design. Is that going to be enough to detect the difference of 0.256? Probably not. If I'm looking at individual differences, I would have to go through and let's say for this, I ran it here. Okay, so if we go through and we take the average of the variances across each one of these vignettes, and we take the average, we end up with a pooled standard deviation of 1.051. Okay, so if I take 0.256, and I divide that by 1.051, it gives me an effect size of 0.24, right? That's consistent with a small effect for a between subjects effect. Now maybe, right? Anybody have G-Power on their computer and stuff? So if you go t-test, that's right, go to, t-test, and go for your statistical test, go to mean difference, 2 independent means, 2 groups, right there, the 2 sample test, and effect size 0.24, and just change power to 0.8, and then just calculate that. Yeah. How many people do I need in each cell?
274.
274 people, right? To detect that effect if this effect size holds true, that's what we would need to do in order to detect that effect at least 80% of the time, right? So 274 times 8, I need over 2,000 people in order to detect that in terms of a between subjects effect if I was running this design that way, right? Now, instead, 231 is a big sample, is not $2,000, right? And so what we can do is just have the same people running the same thing, and so for a fraction of the cost to run this, very easily capturing this effect versus having to run this as a between subjects design. So now there are concerns here with carryover, and so we have to go through and counterbalance so that making sure order effects aren't going into play. But seeing sort of the intense power of these repeated subjects or repeated measures designs in formulating your questions and things, if you can use these, it's a nice thing to do as opposed to sort of running things in a between subjects fashion. All right, questions on this? All right, cool. So, jumping back into lecture stuff. All right, so this is our, to this point we've talked about one-way repeated measures ANOVA, right? It's just our one-way designs, sort of moving forward here. What we can start to do is start to put together mixed designs where we have both within and between subjects factors, right? So I've seen, on average, we're seeing that this inpatient treatment for depression is having big effects, right? But maybe I want to see whether or not those effects are different depending on, say, gender or diagnosis, right? And whether or not someone has other disorders outside of just depression. Or is this treatment equally effective for people who have had past suicide attempts versus those who haven't, right? Or any number of different questions that I might ask, right? For our, this thing that we did here, right? Maybe we're seeing differences based on some other characteristic. We'll go into next, sort of some other sort of characteristic that we'll go through and put people in, right? Now all of a sudden we've got both a within subject factor and a between subjects factor. And these start to get into some elegant and very interesting, but more complex designs, because all of a sudden what we're doing is we're starting to siphon off portions of variability off into different areas. So if we're talking about a between by within subjects, a mixed factorial ANOVA, what we've got in this case right here is an A by B repeated measures factorial ANOVA, where A is our repeated measure, factor B is our between subjects measure, and so we're going to get three different effects, right? So we can say, do our scores differ across levels of factor A, collapsing across repeated assessments? Excuse me, A is our between, B is our repeated measure here, okay? So let's say, and so we'll get into this with the example the handout that I give you here. So instead of just looking at within this inpatient unit whether depression scores decrease over time, we've got three different units, right? And those three different units are serving maybe different populations or doing slightly different variations on things, right? So the question is does unit have an impact on how these scores pattern over time, right? So my main effect here of factor A, do scores differ across unit, collapsing across our repeated measures? Okay. So this is saying, if we collapse across repeated measures, do we see average differences in unit A versus unit B versus unit C, or unit 1 versus unit 2 versus unit 3? This is often not an interesting question, because we're saying, irrespective of sort of what your measures are, if we average your measures, all your measures together, do we see that this group scores differently than this group, and this scores differently from this group? Often not the focus of what we're trying to do, but it's a question. We also get a main, and so this is going to be your main effect of your between subjects factor. Do scores vary across repeated assessments of factor B, collapsing across group? Okay. This is your main effect of your repeated measure. So irrespective of what unit you're on, do we see changes or variability in the repeated assessments over time? So if we ignore your unit that you're on and just group everybody together, do we still see changes over time? Okay. And then we've got our interaction. This is often why you're running this analysis in the first place. Do your repeated measures scores vary as a function of group? Do we see a different pattern of scores for unit 1 as compared to unit 2 as compared to unit 3, right? What is this question here? What are we asking? What type of question are we asking here? Moderation question. Anytime we're talking about an interaction, we're talking about a moderating effect, right? Does hospital unit change the pattern of means that we're seeing over time? Does hospital unit moderate the pattern of means over time? Okay. And so, depending on so if this is our data and sort of our summary table here, right? We've got our sum of squares total. This is still the same thing as we calculated before. This is just this squared deviation scores of everybody's individual score from the grand mean, right? This is just all the variability in the set. This is the total piece of the pie. Okay. Then what we're going to do is we're going to, again, subsection this off into between subjects effects and within subjects effects, right? Or between subjects variance and within subjects variance. For your between subjects variance, you're going to get the mean of each subject minus the grand mean. So this is for group 1, group 2, group 3. This is person means here across each one of these repeated assessments, right? So we're going to take person's 1 average across repeated measure 1, 2, 3, 4, and subtract that from take the deviation of that from the grand mean and square it. Person 2's average across repeated measures, deviation from grand mean, square it, right? So we're getting on average these individual differences, right? This is our between subject stuff across repeated measures. So average score across assessments, how much variability do we get across individuals? And so this is our between subjects, right? But then what we're going to do is we're going to take that between subjects variability and we're going to partition that up into things that are attributable to group versus stuff that's not accounted for, right? So your sum of squares group here is going to be based on your group mean minus the grand mean, right? So what's the variability in group 1's mean collapsing across repeated measures from the grand mean, group 2's measures from the grand mean, group 3's from the grand mean? So we're taking that between subject variability and partitioning it off and saying what can we, of this variability that we're saying is due to individual differences, how much of that can we attribute to group? Okay. And then over here, we can go through and get our sum of squares from our repeated measure. This is going to be our mean of our repeated measure for each repeated measure here minus the group mean. So this minus this minus this deviation, that minus that minus that. So square deviation. So what we're looking at is our repeated measures across our or variability in our score relative to our grand mean across repeated measures, right? And this is going to go down here. We're going to get our sum of squares cell. This is kind of this is the same thing as our within subjects, and then we're going to use that to get our repeated measures, or our sum of squares for our repeated measure by group. So our within subjects here, we get variability that's due to just across everybody. Repeated measure 1, repeated measure 2, repeated measure 3. This is our main effect of repeated measure. Collapsing across group, do we see variability on average scores across our repeated measures? Here, our sum of squares, this is our sum of squares for our repeated measure by group. This is our interaction term, right? Do this, and we get this by subtraction, right? We take our sum of squares cells, which is the same as our sum of squares within subjects, subtract this, and then we subtract, our sum of squares repeated measure for our group is our sum of squares cell minus our repeated measure minus our sum of squares group. Is that right? That doesn't make sense. Angela, can you have me go back through and check the interaction terms on this just to make sure things are right? But essentially, start to see how and where these different sums of squares are going and kind of what they are incorporated with, right? So here is variability due to your individual groups collapsed across repeated measures. So this is your sum of squares that's attributable to your main effective group, or your main effective between subjects measure. This is error variability that's left over. Then in your repeated measure, you got repeated measure, so your main effective repeated measure. So collapsing across groups. Do we see differences at time 1, time 2, time 3, time 4? Is there variability there, or are they all the same? right? And then we've got variability due to our interaction, the extent to which within each individual group, those repeated measures change over time, and then are repeated measured by our subjects within group. This is our error term for our repeated measure stuff. Okay, so it starts to get more complicated. I gave you a handout that goes through and breaks some of this down. Definitely worth going through and taking a look, making sure that sort of all this stuff makes some sense. This will start to become important when you start looking at calculating your omega or generalized omega squared and partial omega squared based on your repeated measure. You're going to have to take a look and make sure that you've got. Did I give that to you last time? Okay, I'll post it up so you guys will have it. It's just one page. This will start to become helpful when you're trying to figure out exactly what variance components to start to come through and plug in for your calculation, generalized eta squared, partial or generalized eta squared, and partial omega squared, stuff that's going on in that Bateman article. Because the formula is going to depend on the characteristics of your design, so you're going to want to pay attention to that. Questions about sort of this? There's a lot to take in. I don't expect you to look at it and be like, oh yeah, for sure. But go back through, do take a look so that you make sure that you know where this stuff is going. Okay? So for our mixed factorial designs, assumptions, we got now assumptions for our between subjects factors and our within subjects factors. For our within subjects or between subjects factors, we have normality assumption. Laura, why do I have that asterisk right there? What's our normality assumption for our between subjects effects?
Between subjects?
Yeah.
I mean, it's all the same subjects.
Well, now all of a sudden we got a between subjects factor, right? So I might have.
Oh, because you're going to violate it.
Well, I don't know if I'm going to violate it, but normality in what? What am I concerned about here?
And the variance between groups.
When we're talking about our what our group-based design, what's our assumption of normality pertain to? It's the distribution of sample means, right? So once again, anytime we're going through and we're doing these screenings, right? We have a normality assumption. The assumption of normality is that we have normality in the distribution of sample means, not necessarily the distribution of observed means, right? And what two things make our distribution of sample means start to become normal very quickly? What do you got? Give them to me.
Normal population.
Normal population, or
Large
what?
sample size.
And large sample size, right? So again, when we're thinking about do I have a concern with the normality in group 1, group 2, group 3? This is what we're talking about: normality and distribution of sample means, and then homogeneity of variance across groups. I'm assuming that across groups, I have equal variability across each one of my groups and each one of my assessment points. Right? Within subjects, again, normality, but again, this is the assumption that pertaining to the distribution of sample means, not the observed scores themselves, right? So wanting to take that into consideration as we're screening, not to say that wacky distributions can't cause us problems if they're small sample sizes or we have huge outliers within a small sample size, something along those lines, right? But some flexibility there. Homogeneity of variance across intervals, right? So for each group, we want the homogeneity of variance to be reasonably equal across repeated assessments, and then our sphericity assumption, just as before. Okay. So, in our example here, we're going to go through a couple of them. Take the same examples, the same data sets, and just layer in a between subjects factor here. So for our inpatient sample, we're going to ask. So we're going to go through and we're going to have programs. So we've still got assessment at intake, 2 weeks, 4 weeks, and 6 weeks, but now we're going to layer in 3 different programs, right? And our question is do depression scores vary over the course of 6-week inpatient hospitalization? Kate, what's this question, what effect is this first question pertaining to?
The main effect of the repeated measure.
Ah, fantastic. I would high five you if I wasn't put it over here. You're exactly right. Repeated measure across the main effective repeated measure, right? So collapsing across groups, do we see scores vary over the course of the 6-week inpatient treatment, right? Second one, do overall depression scores differ across treatment program? John, what's this effect referring to?
The
Main effective group. And so this is a little bit tricky. So it's saying collapsing across repeated measures, right? So if we average repeated measures across the time 1, 2, 3, and 4, do we see on average that one group is scoring higher or lower than any other group, right? Now for this doesn't make, main effective group doesn't mean much in this example, right? Because maybe if one group was overall higher scores, right? If we get something where we see that, so this is group 1, and this is group 2, and this is group 3, right? Here we would maybe see a main effective group, because if we take 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, right? If we take the average of each one of these groups' scores and take the average of this, right? Something like that. Then we're saying we collapse across repeated assessments. This group on average, their overall profile is higher than this group, right? Which within the context of these data doesn't make much sense, right? Or isn't terribly informative necessarily. But it's a question that we're testing here from the data. We see what the main effective group is getting at here. So this one is, do scores vary across, do our repeated measures vary collapsing across group? And our main effective group is, do our groups differ collapsing across repeated measures? And then our last, does the pattern of depression scores vary based on treatment assignment, right? So is the pattern of scores we see across our repeated measures, do we see a different pattern of effects, whether or not we're talking about group 1, group 2, group 3? This is our moderation effect, this is our interaction. Okay. So this is our ordered means, and then for our unordered means, same type of thing. Does willingness to befriend vary within person across different traumatic events? Here we're just going to restrict it to the 4 trauma vignettes, right? And so this is our main effect of our repeated measure, right? So collapsing across, so what we're going to do here is we've gone through and got people's ratings for each one of our trauma-related vignettes, but previously, based on a different measure, we separated people into 3 different profiles, right? We've got people, and this is based on their general beliefs about trauma and its consequences. We've got a group that is negative, that says, yeah, people are exposed to trauma are dangerous and likely to stab you if they get half a chance and are crazy and they need to be locked up. A benevolent group that's nice. These are people like, oh yeah, they're probably good people and so they deserve the same chances as everybody else. And then 3, an interpersonal group that says, oh yeah, they're probably fine. Just, I wouldn't want to date somebody who's been exposed to serious trauma, or I wouldn't want to, I'd be hesitant to hang out or work with someone exposed to serious trauma because I'm just not sure about that situation, right? So what we've done is we've separated people into 3 different groups and then had them go through and rate these different vignettes. And so here we're saying, do we see differences across these 4 different vignettes collapsing across belief profile? And then our main effective group, and this is a little bit different, right? So does overall willingness to befriend differ across belief profiles? Is this an interesting question? What do you think, Layla? Main effective group. Is main effective group interesting in this? I don't know. And when you're thinking about it, what do you think?
I don't think so.
You don't think so?
Because the groups are like negative, benevolent, and interpersonal, right?
Mhm.
Well, I guess you're less likely to befriend someone.
Yeah, right. I think it's interesting, right? In this situation, whereas before, right, where we've got treatment over time, right? Like, and so I don't know what BDI score over the course of average BDI score over the course of treatment means in terms of something useful, right? But here, we're saying, do we see differences across these groups collapsing across vignette, right? But if our question is, so these are so kind of what people are saying in terms of their believing, how does that translate in their actual behavior, right? Then all of a sudden it kind of starts to go, well, collapsing, whether or not we're talking about people who've been involved in car accidents, combats, sexual assault, or disaster, do we see these groups start to report differences in terms of their willingness to go through and help out and things along those lines, right? So in this situation, I'm kind of interested in this between subjects factor, right? It says, irrespective of what vignette they're responding to, do we see differences across these profiles in terms of people's willingness to offer help to the hypothetical individual? So I might take a look at this. And then last, this is our interaction term. Does a belief profile impact the pattern of friendship relations across response to these vignettes? So again, the same data, we're just throwing in a between subjects factor, so we're going from one way to a mixed factor ANOVA here. So let's go through and take a look at our BDI data first. Okay. So here, and again, this is going to correspond to your your handouts, your 3x4 repeated measure ANOVA, your ordered means. So before we jump in, I'm just going to go through and clean this up because program is our between subject factor. And if I sort this, I see I don't have program data for 23 cases. So I'm just going to nuke those folks. With this design, it wouldn't include them anyway, but just so everything's clean, so I'm making sure everything's on the same page, I'm just going to get rid of those. And so what I'm going to do is I'm going to go through and we'll analyze general linear model. I'm going to go down to repeated measures and call this time. Oh, I've already got that punched in. I don't want to screw it up. Okay, but we've got factor one. We've got time as factor one, right? This is just based on what we've done before. If you shut down SPSS, it probably won't have it. You have to put it back in. So nothing different that we've done here. We'll go ahead and define. We've still got BDI 1, 2, 3, 4 in terms of our repeated measure assessment. But now what I'm going to do is I'm going to take program, our between subjects factor. I'm going to drop it down here in between subjects. Okay. Now, if we had some sort of covariate, right? I wanted to control for extroversion or some continuous covariate or something like that. We could drop that down into this covariate box. That makes our design more complicated. We won't do that, but that's what that might look like. But if we go up, model's going to stay the same. We're not going to worry about that. Contrasts, this is still going to be our within subjects contrast. It's going to give us, it'll still give us our polynomial contrast, but so we'll leave that there. Plots, let's change our plot a little bit. So we're going to remove that, and we're going to put program as separate lines, time on the horizontal axis. What this is going to do is it's going to give us different lines for our different programs, right? We don't know if we're going to get an interaction effect in this data, but we're going to have SPSS plotted out just in case it comes up, okay? Then I'm going to go down, I'm going to hit add, continue, post hocs. Now all of a sudden I can start asking post hoc tests for my effective program, right? What is this going to test? What are these post hoc tests going to correspond to? Yeah, it's just going to be collapsing across my repeated measures assessment. Am I going to get, so that it'll do post hoc differences across this. Now for this question, this really isn't an interesting thing. But if I wanted to go through and do, I could go through and select all of my different options there for post hoc tests for that. We won't worry about that here. I'm not going to save anything, but in terms of options, right? I might go through, and this is nice, get marginal means for my main effective program, my main effective time, and then my program by time. this is gonna go through and it's gonna give us out, sort of, this is nice for different interpretations and sort of a quick look and try and get a sense for what's happening here, okay? So I'm gonna still ask for my descriptives, my effect size, and then my homogeneity variance test. I'm gonna ask for that. Continue, and I'm gonna hit OK. So, a lot of this is gonna look familiar. We've got our repeated measure, BDI 1, 2, 3, 4. That makes sense, right? Now I'm looking at my between subjects factors, right? I got a between subject factor for program 1, program 2, program 3, right? So it's not a specific, it's not a balanced design, but I don't have horrible discrepancies across these, right? I've got 100 people, 101 people in my smallest group. I've got 141 in my biggest group. It's not the worst, it's not perfect, but something to take note of, okay? Now, what have we got here? Haley, tell me what we've got going on in this, in that table right there.
In the descriptives?
Yeah.
I mean, it's separated out by program within each time period.
Exactly, right? So we've got 4, intake, mean standard deviation program 1, mean standard deviation program, or time 2, mean standard deviation, or excuse me, sorry about this, at intake, mean and standard deviation program 1, mean standard deviation program 2, mean standard deviation program 3. Same thing, 2 weeks, 1, 2, 3, 4 weeks, program 1, 2, 3, program 6, 1, 2, 3, okay? What does, if I wanted to see my main effect of repeated measure, what means are those going to correspond to? Okay.
For the repeated measure, like BI at intake 2 week and.
Yeah. Which mean those specifically in here?
Is it total?
What's up?
Each one?
The total, right? So total here, total here, total here, this is total here, right? This is the mean at each time point collapsing across group. All right. And so if we're going through and we're thinking about screening, right? So in screening these data, we would go through and we would sort of separate. How would we separate these? How many groups would we split our file into? 3. And then how many repeated assessments do we have? 4, right? That's a lot of cells to screen and go through and take a look at distributions and then things along those lines, right? So screening for these factorial designs is actually, there's a lot of stuff to take into handle or take into consideration, right? And so if I'm going through and I want to think about whether or not I violated a year and a day to get all this stuff. Okay. So if I was going through and screening these data and wanting to check homogeneity of variance, because already I have equal cells. Those aren't the same, right? So that's something I want to take into consideration, right? And if I go through and I take a look at the distributions of each one of these, I'm probably going to find problems with normality in cells. Now, if I find that that my cells are looking a little funky, am I too concerned about that? Why not, Evelina?
Do you have multiple cells?
you have multiple cells, but what is it? So let's say that I find, even when I go through and I look at, so we've got 12 different cells, even if I find that my actual scores within those cells are really pretty skewed, am I too concerned about that? Why not?
Is it because we're assuming that we're gonna violate sericity?
No, but we are going to do that. What about this design makes me more comfortable if I have even cell distributions that are looking gross?
You have a big sample size?
Yeah, I've got big sample. Like my smallest cell size is 100. At samples of 100, my distribution of sample means it's still going to approach normality very quickly, right? So it's something I would want to note and say, boy, cells look non-normal based on this or something like that, but probably not going to be as concerned about it, right? I might also find maybe outliers and extreme values. That could happen, and it might if you go through and if we were to go through and take a look at this. Are we concerned about outliers and extreme values, Layla? Okay. And I think not sure that we couldn't be, but we're likely pretty robust to outliers and extreme values for this. Why? Because those cells are pretty large, right? If I get one squirrely score in a cell of 100, you're probably not going to do a whole lot, right? If you think about BDI, scores ranging from 0 to 63, it's a pretty big range, but it's not like we're talking about income where someone could be several orders of magnitude above sort of where everybody else is. So we'd want to go through and take a look, and if we found stuff that looked like extreme values, we'd want to go through, follow up, make sure that those were plausible values, right? But maybe not something that we would be necessarily concerned about. So we won't go through, we'll do this with the other one. But then the fourth thing I might be concerned about is our homogeneity of variance. Okay, and so for here, what I would want to do is I'd have program 1, program 2, program 3, right? And I've got base, 2 weeks, 4 weeks, 6 weeks. Then I'm going to have a variance component here, variance component here, variance component here, right, across each one of these. What I would want to do, just to check everything out, is go through and take a look at F max, look at differences across time 1, right? And then F max, look in between differences at time 2, and then F max at time 3, and F max at time 4. Okay. Am I done? No. What else should I be doing, Evelina? Yeah, looking across these, right? Because we have assumptions about homogeneity of variance, both within and across, with both across groups and across time, right? So I would want to go through and look at F max here, F max here, F max here, right? And what I'm looking for is really, really massive ratios between the largest to smallest variance across my groups, right? And then also across within time points.
So the rule of thumb for that is if it's under 3, you're okay.
Yeah, and then it starts to come through. I mean, and Sebastian and Fidel talk about F max, exceeding 3. And I mean, basically you're saying that you've got the ratio of the largest variance and the comparison is 3 times the size of the smallest one. Right? You got a 3-to-1 ratio there. If you've got equal cells, you'll probably be okay. But if you've got unequal cells, this is where we start to worry, right? Because if I've got a massive, so very, very large variance in a very small cell, right? Well, that small cell doesn't get much weight into the whole thing, right? So we may be underestimating the variance, right? Or if we've got my biggest cell has a lot smaller variance relative to my sort of the other ones, but it's got the most people, and so then that's going to go through and weight more heavily in sort of our overall mean squared errors and things like that, so it's going to maybe underestimate. So this is where variability or the cell size starts to have an impact. If we've got equal cells, then no one cell is going to have more or less influence on our overall estimate. Still not great, but I'm less concerned versus when I have unequal cell sizes. Now here, I'm going from 101 to 141. It's not huge differences, but it's, I don't know, right? And so if it's something that starts, there's no rule of thumb, right? There's no like, oh, at this is a point when things start to fall apart. But something you would want to know in terms of your screening stuff.
Are we picking the lowest and the largest to compare, and then within program we're just doing base and end?
No, all of them, right? So
Okay.
at time one, or at baseline, right?
Yeah.
What's the ratio of the largest to smallest across these? And then at time 2, and time 3, ratio of largest to
Right.
smallest, and it's the same thing here, right? And then at for group 1, right? We're looking at sort of ratio of largest to smallest,
Okay.
largest. So what you don't need to do is identify within the whole matrix the smallest to the largest. Don't worry about that, right? Just focus on across groups and within across assessment points. All right. So these are some things we want to go through and think about in terms of screening stuff. But if we go down through and take a look at these data, want to make sure your descriptives are looking good. Like that's all where it needs to be. This box tests of equality of covariance matrices. Don't worry about that. You don't need to concern yourself there. Multivariate tests, again, we're not worried about that, so we can ignore that. Sphericity, we're assuming that we violated sphericity. We can ignore that. And then our tests of within subjects effects. John, what do we? Give me an interpretation of what's going on with our tests of within subjects effects.
Looks like there's a significant effect for a repeated measure. And then,
Okay, stop right there. So we do have a main effect of our repeated measurement. So what is that telling us?
It's in regardless of their
Right. Well, we don't know if they're improving yet, but that's based on the previous. It's what we would expect, right? So main effect of time, or main effect of our repeated measure, is just saying that collapsing across groups, we're seeing variability in our means over repeated assessments, right? Okay. And then what else are we seeing in there?
Also the
The interaction is reliable, right? And what does that mean?
just that it's telling us that one group is
Yeah, want to keep them more general, because based on the omnibus effect, we can't tell, we can't say whether or not anybody's getting better or worse. There's a lot of different ways that things are going through, right? But what we can say, though, is based on this interaction effect, it's saying that the pattern of means or the variability of means across repeated assessments is different for at least one group versus the other, right? We're saying that grouping factor makes a difference in determining the pattern of means, right? Now, even though we kind of have a good sense for what the pattern of means looks like in here, it could be all over the place, right? Like maybe one group sort of starts low and then gets high and then goes low, and another one gets low in a different way, or then one is just flat and doesn't get changed at all. I don't know what it looks like, right? But all this is saying is that main effect is saying that on average, collapsing the cross group, we're seeing variability in means across repeated assessments, right? i.e., they're not all the same, right? And then but what we see, and we'll get into this a little bit, and we talked about this before with our between subject designs. Can I make a strong interpretation about this main effect here? Not really, and I want to be careful about interpreting this main effect, because that main effect is conditioned by grouping factor, right? So the main effect here isn't actually a main effect, it's a conditional effect, right? Because what we see is that that pattern of means, or the pattern of scores across repeated assessments depends on whether or not we're in program 1 or program 2 or program 3. The specific pattern of means is dependent on a grouping variable. Okay. People kind of get in, and then we've got our partial A squared to our omnibus effect here. Main effect, or this conditional effect, is accounting for the greatest proportion of variability in our outcome. Our interaction, a much smaller piece of it, but it is statistically reliable in these data. Questions about this? Okay. Then we go down and we've got our tests of our within subjects contrasts. I wouldn't worry about this too much. We've got our Levine's test. All right, what's our Levine's test telling us here? Laura, if you look at this Levine's test, what would you guess? How would you guess we would interpret this?
I would guess that it's telling us it's across the different groups at each time point.
I will give you a high five. Yes, absolutely. This is like as if we were to run separate one-way ANOVAs at each one of these time points, and we'll run our Levine's test at each one of those. These are the results we would get, right? So it's saying, and this is pretty impressive too, because we've got pretty big cell sizes, that we're not seeing evidence for reliably different effects or reliably different variability. Variability across groups is looking pretty similar at baseline and 2 weeks. When we get into 4 weeks, it's statistically significant. Why might I not get too worked up about this?
I think we're going to evaluate.
Okay.
Or we expect to see change with treatment.
We expect to see change. So, and again, that's kind of getting into this idea that, you know, it's not necessarily we're not expecting it. But just because we're not expecting it doesn't mean it can't cause us problems. What might start to make me be a little bit, what should I be taking into context when I'm interpreting the significance of the Levine's test here?
They're in different programs, so it's going to be different anyway.
Okay, so they're in different programs, and again, that makes some sense, but at least that's kind of irrelevant for my statistical test, because my statistical test is based on the assumption that it doesn't matter that even though they're different populations, that the variance is equal, right? What's going on in these sets that makes me sort of not be at least sort of flying out of my seat to see that I violated the homogeneity variance here? How are these tests? Are these highly powered or not so great powered tests? Got a whole bunch of people in this design, right? Just because something's statistically significant doesn't mean it's necessarily a problem, right? Just because everything's not, same thing skew and kurtosis, just because my skew is not 0 doesn't mean that I necessarily have a problem, right? And so thinking about, and again, this is where you start to want to take into context features of your design and making your interpretations, is because I've got a ton of people. I've got 300 some people in this design, right? So these are probably pretty sensitive tests, right? So I'm wanting to take this into context with your F max, right? And say, well, it's statistically significant, but we've got 100 people in my smallest cell and 140 in my largest cell. It's a pretty sensitive test, right? So I'm probably not going to be too worried about things. Here, by the time we get to week 6, we do see sort of more stuff, and so we probably do have a violation of homogeneity of variance within the context of this design, but whether or not it's something huge, maybe not, but this is something that's going to start to make me think as I start to think about how to tease this apart and how I want to go start testing and testing effects. This is probably going to say, well, I might be less confident just pulling the terms from my overall ANOVA table because we do have some violations, some different cell sizes and things along those lines, okay? But we see here that we do have, or no we don't, our test, our main effective program here, this is saying that just collapsing across repeated measures, do we have differences in our overall BDI scores across program? Not really, right? I mean, not anything I'm going to be too worried about. It looks reasonably comparable, right, here. So what we do have is evidence of a main effect of our time, or a main effect of repeated measure, but that's a conditional effect because that effect is dependent on what group we're talking about, right? The pattern of means across repeated assessments differs based on what group we're talking about. And so if we go down and we take a look, so we've got, this is our marginal means. This is why these are nice to print out sometimes. In general, I would be using your observed means just because for follow-up tests and things like that, just because it's the actual observed scores here. But if I look at my main effective program, this is saying on average, mean score collapsing across repeated measures for program 1, program 2, and program 3. If I'm looking at these as BDI scores, am I too concerned that there's lots of differences going on between these 3 groups? Probably not. Those are fairly comparable, right? But if I go down through and look at my marginal means for main effective time, seeing big reductions from baseline to 6 weeks, right? Big jumps, and we had seen that in the last assessment. Then down here, if we go through and we take a look at program by time, this is giving our individual cell means for time 1, time 2, or excuse me, program 1, program 2, and program 3. And once again, if we run any type of these types of tests and we get a significant interaction, what's the very first thing we do? Think about that. Non-effect size.
Graph it.
What's that?
Graph it.
Graph it. Plot it out. We want to see what it looks like. Now, SPSS does it for us, but it's kind of a cruddy graph. But we kind of get the gestalt of what's going on here. And if we look at this, right, we see kind of what's going on, right? Within the context of these analyses, in general, it looks like scores are changing and getting better across all 4 programs. But the specific pattern looks like it's a little bit different depending on what program that we're talking about, right? Now remember, this is a big sample. We've got lots and lots of power in this, right? And so it doesn't look like there's, I mean, just eyeballing it, it doesn't look like there's a whole lot going on, right? But there are reliable differences, it looks like, on average, in terms of where people are at in terms of program, okay? Now this goes back to this question, should I interpret that main effective time in the presence of a grouping effect? Some people will freak out and get real rigid about this. You can never make an interpretation of a main effect in the context of an interaction. I would say, yeah, probably most of the time you can, because you can't get a very precise estimate. You could say, on average, collapsing across everybody, we're seeing a reduction in means across repeated assessments, right? But the exact nature of that difference is going to depend on what group we're talking about. But if this is, again, an inpatient program, and we've got different groups, right? Is it worthwhile interpreting the main effect of time here? Yeah, why would you say yeah?
Because it looks like program 3 has a much quicker reduction
Uh-huh.
when baseline to what, 2 weeks?
Uh-huh.
And then also overall, just to get
Yeah.
lower scores.
But if we're just talking about the main effect of program, is that something worth interpreting within the context? So collapsing, main effect of our repeating measure. So collapsing across program, is there value to interpreting this main effect of time or repeating measure? Yeah, why?
Because it can show how like symptoms can like reduce over time. It's still valuable.
Right, right. So for this, and again, one to always think about and not sort of get stuck on hard rules. If I was doing a program evaluation for this hospital, right, and I wanted to say, the question is, from the hospital standpoint, are we doing our job? Are people getting better as they're going through our program? Yeah, I'm going to want to. In this situation, I'm going to say, in general, people who are participating in this program are experiencing massive reductions in depressive symptoms, right? So irrespective of what program you're in, on average, people are getting a lot better, right? Now, that pattern of repeated assessments over time, and notice that I'm trying to keep from saying change or reductions and sort of trajectory and things like that, because again, we're not looking at that with these analyses. These are just looking at mean here, mean here, mean here, mean here. And so technically, we're not looking at trajectory of anything, we're just looking at pattern of means, right? But depending on what program we're in, that specific patterning of means or the variability in scores over the course of treatment look different in some ways. But overall, I'm still saying that this main effect of time is important because it doesn't matter what program you're in. People who come into this program are doing much, much better by the time they get out than when they came in. Now, sort of what that looks like depends on what program they're in, but overall, sort of wanting to take a look at this, right? So same thing, thinking about interaction terms like does gender and sort of family history impact the relation between smoking and health outcomes, right? I might find an interaction effect there, but if my main effect says, yeah, smoking causes negative stuff on your outcomes, and that's a big story, then even though it's a conditional effect, I still want to interpret it because, yeah, smoking is bad for you, don't do it. Now, that conditional risk differs depending on certain other types of things, right? So I can't give you a specific answer on how bad is smoking for you. Well, it matters, depends on some other stuff, but sort of wanting to think about sort of context and things like that. All right, cool. Yeah, John.
And then for like the problem set, it says the graph results in the style, so it's basically scaling this table.
Which, I'm sorry, what was that?
Like in the problem set, it has like a graph.
Yeah.
Basically saving this table.
Yeah, going through and just give me a graph that's not SPSS. Okay, awesome. Thank you, folks. So what I'll do, and Evelyn, if you need to just get out.
Yeah, we're just gonna-
Yeah, no problem. Go. What I'll do, so we still, I think.